Greetings and welcome back. Today we're going to be looking at both condensed formulas and line angle structures. These are two ways to more effectively and clearly communicate the structure of an organic molecule. As you've probably noticed, line angle structures can get quite cumbersome as you're drawing out lots and lots of hydrogens and carbons and oxygens, etc., 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 especially for large biomolecules. So today we'll be looking at two more exact ways to communicate a structure than molecular formulas, but also two more concise ways to express the identity of a molecule than a Lewis structure. So first I'm going to start out with a question, which is that let's draw a Lewis structure with a molecule that has the molecular formula of C3H8O. Alright, so to start this out, just like drawing Lewis structures, we have three carbons, 8 hydrogens, and an oxygen. So we should save the hydrogens for last and put the carbons and oxygens together. So let's start with that. The simplest way to do it is to put a carbon on one end, attach it to another carbon, that's two carbons, put in a third carbon, and then lastly our oxygen at the end. All right. If we notice, we have, let's count them, 1, 2, 3, 4, 5, 6, 7, 8 spots for hydrogens, so we can go ahead and draw our hydrogens in. And this would work out perfectly, and we would have one correct answer to the question of draw a Lewis structure for C3H8O. All right. However, we have another correct answer to this question, which is that we could draw out our three carbons in a row again, but instead of putting the oxygen on an end carbon, we could put the oxygen on the middle carbon. Right. Once again, let's count up our spots for hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. Again, the reason that we do that is instead of drawing in hydrogens all around, if we count them before we draw them in, we can tell whether or not we need to make a double bond or a triple bond or something like that. But since our number of unfilled bonds is equal to our number of hydrogens, we don't have to do anything like that. We can just draw in our hydrogens. And once again, the math works out nicely and all of our hydrogens fill in. Well, these are two different structures. So C3H8O, as we're seeing, is not the most effective way to communicate exactly what a molecule or what a structure could possibly be. Drawing these Lewis structures is much more correct. That top structure and the bottom structure are indeed different. Furthermore, there's another way to draw this out, which is instead of putting all three carbons in a row, we can put two carbons in a row and then put the oxygen, and have another carbon at the end. So this is kind of like the top one in that it's a straight line of everything, except that instead of being three carbons and an oxygen on the end, it's two carbons, and then an oxygen in the middle, and another carbon. Well, if we count out our spots again, there's 8 places for hydrogen, so I'll draw all of those in. And this is another correct Lewis structure. And all three of these are C3H8O. So all three of these would be a correct answer to the question of draw a Lewis structure of C3H8O. But as I mentioned again, these are all three different structures. And as we start to have more and more carbons, the number of molecules that could possibly represent C3H8O, C4H10O, 2, etc., 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 goes up astronomically. So what we need is an effective way to communicate exactly what these structures are that is not just a Lewis structure. Again, Lewis structures are good, they work, except that it's very cumbersome to draw all of that stuff out. So let's look at another way to do this, which is the first thing I mentioned earlier, condensed formulas. So a condensed formula, what that does is it essentially takes one chunk at a time, going down the molecule, and basically turns it into an extended molecular formula. That is to say, instead of just saying that we have 3 carbons and 1 oxygen and 8 hydrogens in the molecule, we can say that we have a CH3, which is what we have on the left. Right? This right here, what I've circled, is a CH3. And then right next to that, we have a carbon with 2 hydrogens, or a CH2. And then we have a carbon with 2 hydrogens again, or a CH2, followed by an OH. So CH3, CH2, CH2, OH is very similar to a molecular formula, right? This up here is a molecular formula, except that it's much more clear. It tells us that I have a carbon with 3 hydrogens, followed by another carbon with 3 hydrogens. Oh, sorry, carbon with 3 hydrogens, followed by a carbon with 2 hydrogens, followed by a carbon with 2 hydrogens, and then an OH. This tells us exactly what the molecule looks like. Furthermore, we condense this even more, or we can condense this even more. You'll see that we have 2 CH2s in a row. So instead of writing both of those out, we could say that we have a CH3 followed by parentheses CH2, 2, indicating that there's 2 CH2s in a row, and then an OH. So one of the great things about condensed formulas, and again these are condensed formulas over here, is that condensed formulas can be typed out very easily, whereas Lewis structures cannot. So if you are writing a journal article or something like that, or just typing things out using your computer, it's much easier to express condensed formulas. You'd have to download some type of chemical drawing program in order to draw Lewis structures. All right, so let's move on down and look at the condensed formula of our next molecule. Our next molecule has a CH3 again, which is directly attached to a CH, and it has a branch up here. It has kind of a branched OH up at the top, and then another CH3. So the way that we could express this would be to do a CH3 followed by a CH, and for a branch we put it in parentheses. So parentheses OH, indicating that that OH is attached to the CH, but what's not in parentheses is part of our main chain. So we would say that we have a CH3 followed by a CH. Then we have this branch coming off, but then let's go back to our main chain, which is down here, and we would close parentheses and move into a CH3. And that would be the condensed formula of that middle structure. The bottom one is probably more simple than the second, which is that we have, again, a CH3 followed by a carbon with 2 hydrogens, a CH2, followed by just an O. And this is not branched, it's just along the chain, followed by a CH3. So those would be the condensed formulas of these structures. While the molecular formula, which is C3H8O, is the same for all of these molecules, the condensed formulas are different. So the condensed formulas are much more easy to write out, they're much more easy to type out, and they express to us the exact identity of the molecule. Lastly, let's jump into line angle structures. Line angle structures are even simpler, all right? But let's start once again with some Fisher projections, turn them into condensed formulas, and turn them into line angle structures. All right, so in this case what we're going to do is draw kind of as many possible structures for C6H14. So this is 6 carbons and 14 hydrogens, which will be a relatively large molecule. So let's start out just kind of putting all 6 of them in a row. So if we put our 6 carbons in a row and count up the number of possible hydrogens coming off so that each of our carbons has 4 bonds. If we count these as we go along, you will notice that there are exactly 14 of them. And again, they'll take the cumbersome time to draw in all of our hydrogens so that we have a correct Lewis structure. You're welcome to pause this, by the way, and see how many of these you can do on your own. But I'm just going to kind of keep going on these. So that is 6 carbons in a row. The way to express this in terms of a condensed formula is, once again, we would have a CH3 at the end, followed by CH2, 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 and another CH3. So if we wanted to represent this as a condensed formula, we could write CH3, and then I'm going to condense this, which is to say that I have 4 CH2s in a row. So I will put CH2 in parentheses and indicate that there are 4 of those. And then I have another CH3 at the end. So that would be the condensed formula for this structure. A way to do this in terms of line angle structure is that line angle structures are a way of really shorthanding the things that we know already as organic chemists. So the things that we know already or can assume already is that there are hydrogens everywhere. So let's imagine that we cross out all of those hydrogens. Well, this is not a perfect Lewis structure, but just going backwards, we could say that if I drew out 6 carbons in a row, then just told you that there were hydrogens everywhere, you would get the idea that the rest of that must be filled in with hydrogens. So why do I even need to draw those bonds? Why can't I just say that I have 6 carbons in a row? And at that point, why do I even need to say that those are carbons? Of course the main chain of any molecule is carbons. This is organic chemistry. So while you couldn't just draw 6 lines in a row, those are actually 5 lines in a row to join those 6 carbons, because if they're perfectly straight, you wouldn't know if it's one long bond or 5 short bonds. So we can do this. And what that is indicating to us is that you have, at every single corner or every angle along these lines, is a carbon. 1, 2, 3, 4, 5, 6. So this is the ultimate shorthand of a structure, is to say that this kinked line that has 1, 2, 3, 4, 5 bonds, well, every single end of this is a carbon. We know that because we are speaking the same language. Those are 6 carbons in a row, and furthermore, each of those carbons needs to be making the right number of bonds, otherwise they would have a formal charge. So this carbon at the far right, well, that's making only 1 bond that we see, therefore it must be making 3 bonds that we don't see, 2 hydrogens. This one must be a CH2, this one must be a CH2, this one must be a CH2, CH2, and then again a CH3 at the end. So we would never do this. We would also never do this. And we certainly wouldn't even put any of those little kind of CH2s in there, so I'm going to go ahead and erase those. And so that is the line angle structure. All right, so let's draw a couple more and see how we can do these. So let's do another Lewis structure. Let's put, oh dear, it's a big carbon. I'll make that a little bit smaller. All right. 3, 4. And I'm going to put carbon off of this one, carbon off of that one. All right, so now what we will have, if we draw in all of our possible bonds, so you will notice that if we give all of those carbons 4 bonds, once again we would have room for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 carbon, or hydrogens. So therefore this would work out perfectly again. All right, so let's do the condensed formula. So once again we will start at the end and keep going. So we would have a CH3 followed by a CH, and that would have a parentheses CH3 because there's a CH3 coming off of it. Right, and that's this guy up here. Then we would have another CH coming down our main chain. So going back to our main chain there, we would have another CH3 attached to that guy, followed by a CH3. So there are actually multiple correct ways to do condensed formulas. So let me tell you another way to approach this. Another way to approach this would be to say that we have 2 CH3s. They're both attached to a CH. In other words, CH3, 2, both attached to a CH. And then we could do the same thing on the other side. We would say that we then have a CH, and then we have 2 CH3s attached to that guy. So we're doing that same thing that we did previously, which is to summarize things or condense them together whenever we need to. Right, and both of those are correct answers to a condensed formula, and they give us everything we need to know. All right, so let's do a line angle for this guy. A line angle, what we would do is, I'm going to kind of put training wheels on this. We would just draw in our carbons like this. And we don't include any of the hydrogens, so what it ends up looking like is, let's do that main chain right down the middle here. So 4 carbons, so 1, 2, 3, 4, and there would be another carbon coming off of the second one, and another carbon coming off of the third one. And that would be your condensed structures. And your line angles, all together. All right, so let's give that a little practice. All right, so the last thing I'd like to mention for condensed formulas and line angles is that you can also convert condensed formulas directly into line angles, and there's a little bit more to line angles when we're also including things like nitrogens or oxygens. So let's look back at that very first problem that we did, which was that we were drawing out those C3H8Os, and we had a possible answer that was a CH3 followed by a CH2, CH2OH. We had a CH3 attached to a CH2, which had an OH coming off of that, followed by a CH3. And then lastly, we had a CH3, CH2, OCH3. And those were our three structures from that first problem. So let's do the line angles on those. Starting at the top, we would draw out our 3-carbon bond. So that is to say we have a first carbon to a second carbon to a third carbon. We know that the corners of each of those indicates a carbon with the necessary amount of hydrogens in order to give it 4 bonds. Well, the next thing coming off of that would be an OH. So we need to draw another bond, but instead of just being a blank bond, because this would indicate that we have 4 carbons in a row, this last bond goes to an OH. We write the H's on things like oxygens or nitrogens or sulfurs or phosphorus or whatever in there. But the only time we leave the hydrogens off in the line angle structure is if they're directly attached to carbons. So we don't draw hydrogens or carbons here or here or here, but because this is a heteroatom or not a carbon, we write the OH out, and that's it. In the middle one, we do indeed have 3 carbons in a row. But now we have an OH coming off of the center carbon, so we just have a bond up to an OH that looks like this. The last structure has all 4 kind of non-hydrogen things in a row, 1 carbon, 2. The third thing in a row is an oxygen, and then we would have a carbon coming off of that. And so these on the left are the condensed formulas, and these on the right are the line angle structures. As you can imagine, getting to know how to draw line angle structures is going to make your life incredibly easy, because line angle structures, if you can indeed interpret exactly what they are the simplest and concisest, most concise, way to draw organic molecules. All right, thank you very much. Practice this, and I will see you in class.